Funding for this program is provided by Annenberg CPB to advance excellent teaching.
For this age of children, it is necessary that the materials are chosen so that they see with their own eyes how the ball rolls down a ramp.
You have to start these kids off with something that's a little bit more concrete. Then you can kind of branch them off into the abstract and get them to formulate ideas.
And they can begin to put together a pattern and synthesize something that may be totally unique in their analysis.
We get to know each other, we talk about family.
I have to learn about them.
What are their responsibilities to their communities?
All the kids are really good if you just sit down and listen to them.
I rephrased the question. Maybe the question was wrong.
So that they have an awareness, an education, and a tolerance for other cultures.
You improvise every step of the way.
I know what a certain child's best is, and I expect that.
It makes me feel really happy to be a teacher. I'm kind of choked up.
Watching children develop and learn is like watching a miracle in action. One day they're talking and walking, the next they're reading and writing, and the next they're hypothesizing and inventing. How can teachers support each student's developing abilities? How can we ensure that our teaching supports the whole child? I'm Linda Darling-Hammond, and that's our challenge for this session of the Learning Classroom. Teaching in a developmentally appropriate manner means working with rather than against the child's natural learning process. Learning takes place along several critically important pathways.
There is the physical, the social, interactive, the psycho-emotional, the ethical, linguistic, intellectual, cognitive, and it is development along all of those lines that's really important. Up until recently, the school focused on the linguistic and the intellectual cognitive, but it is growth along all those developmental pathways that is important.
Good teachers start from where their students are and build upon what they are able to do. But how do we know what our students are ready for and when? The concept of the zone of proximal development helps us here.
The zone is an important concept because to teachers it's absolutely vital because it helps the teacher understand what is the basic act of teaching. And that is this, to locate that point in the zone of proximal development in which the learner needs the assistance and then to provide it. Good teaching means constantly stretching, moving, rising in the developmental process, and that means always providing more assistance.
Psychologist Jerome Bruner described a spiral curriculum that returns to important concepts at different stages when children can understand them more deeply. In this half hour, we will see 3 teachers guide their students through an increasingly sophisticated understanding of momentum. They provide wonderful examples of developmentally appropriate teaching. Faye McLean, a first-grade teacher at Paddock Elementary School, uses a variety of concrete tools and draws on her students' life experiences to address the concepts of mass, speed, and momentum.
Today we have a very exciting thing to talk about. You'll have to help me think. This is a thinking kind of activity. I think before we came to school it snowed a lot, remember? Did anybody go sledding? This morning is just an introduction of several cycles which will help them understand concepts of motion. For example, the relation of weight or mass with speed, the relation of incline of a ramp to speed and momentum, or the relation of weight with momentum.
We went in my sled together down the hill.
Oh, you used one sled?
Yeah.
Oh, okay. Is there anybody else who has gone sledding with an adult in a separate sled? So who got there first, to the bottom?
Both of us.
Really? Oh, okay. Well, this is an interesting class because I have a book here. What does it say, Colby?
Sledding on a hill, rolling down a ramp.
Rolling down a ramp. So our story starts with a child and a grown-up. and they're going to go down the hill. How do you think they're going to get down the hill?
I think the littler kid will go down first because it probably has much more energy.
Okay, any other thought?
I think the grown-up will get down first because more weight makes the sled go faster.
So we have all these different ideas. Look what happens in the story. They go down and go swoosh.
Whoa.
They get to the bottom of the hill together. That's what the story says. We'll call this the ramp, okay? Now, how are we going to know, or how are we going to remember how long it takes for a ball to go down? Remember? We can't just keep it in our heads because everybody forgets, especially after recess. We want to make sure we remember.
Write it down.
You write it down. For these age of children, it is necessary that the materials are chosen so that they see not just the abstract time, but they see it and with their own eyes how the ball rolls down a ramp. So I have a 6-foot ramp instead of a small ramp because I want to make sure that the numbers are big enough to show difference with the children. It's the same ball. We didn't change the ball. I wonder what's happening here. Okay, let's try it again. I want to make sure that in their participation, they are very clear of what we would call controlling of variables. We called it fair, so that it starts from the same place, and then we time it at the same time until the end.
Stop.
When I plan my activities or units of study, I make the activities or the context rich enough so that it would benefit the children who are quite competent and the children who are not quite so competent in certain areas. If you think you know what you're going to do, come and get a big paper and start. I want to make sure that children who are close to mastery will be able to have tasks that will help them to that mastery, and in their interaction with the children who are just entering the zone, they will solidify or stabilize their competence, and the children that are entering will advance and become more stable in that zone. Look at Mrs. McLean, I forgot one thing. Would you write a sentence at the bottom of each illustration and say what you think in words this time? Hopefully, in the next investigation, they will be at an even higher level, and then the zone is advanced. The next thing that we're going to do is to look at all their drawings and what they wrote and their conclusions of how many seconds it took for the balls to go down the ramp. So they will discuss that, which is part of oral language and literacy. The lower the ramp, the lower the ball, slower the ball goes. When they have to write it down, they really have to think about it. And that's what we want the children to do, not just in science, but to understand informational text, which is what they really wrote, is information about what they did. You're going down there. It's going to hit it. What's going to happen? When we used the long ramp, that's a physical symbol of reality, which is the hill. So I think of that as a concrete operational tool. And it is a symbolic tool. It's a physical tool representing something. When we made the representation of that ramp, and the children drew illustrations of that, that then became a higher level of symbolic tool. It's a graphic illustration or a graphic representation, which they did on their paper and on the chalkboard. And the question you're asking is that, is it true that when the ramp is high, you would move an object farther than when the ramp is low?
Ready?
Wait, look at this. Make sure they're all in the same line. From my experience, these children are not going to be able to look at the data using numbers of measurement to really understand that the concept in this context of the level of the ramp relative to the momentum, and that's how far the can will move.
Come on, come to Papa, come to Papa.
The tracing is more pictorial and is more appropriate to their age. Now, can you look at it and think about the speed of the balls as they went down the ramp, and look at our picture? Actually, people call that a graph, a line graph. I'd like to have you make a picture of it, though. I try to relate it to a form of a story, a narrative that hopefully can relate to their own lives. For me to understand or to assess their understanding of the concepts. In one instance, for example, the two children were working together. Oh, I see, your pictures go together. They drew this picture where one of them won the race with a snowboard, and the other one got a bronze medal, according to him, because he started from a lower hill, so he couldn't go as fast. And the other child, who started from the higher hill, went faster. So to me, they are understanding that the height of a ramp, or the steepness, is related to momentum or speed.
Can you hear me?
Faye McLean finds many different ways to assist individual students within their zones of proximal development. Now let's take a look at how George Mixon presents a similar lesson to his 8th graders at Birmingham Covington School. Notice how he extends his students' thinking by asking them to form hypotheses and examine multiple variables.
If I have these objects, okay, talking about one of them dropping or both of them dropping, okay, are they going to fall at the same rate or are they not? What do you think, Express?
They're going to hit at the same time.
Hit at the same time. How many of you guys agree with Alex? How many of you guys disagree with Alex? You all agree with Alex. Okay, so if I drop them, they should all hit they should hit this table at the same time, correct? What was the rate at which they fell? About 9.8 meters per second squared, okay, or what?
33 feet.
Or about 33 feet per second squared, okay? That's the acceleration in which they fall down. You guys are going to do that same kind of experiment, but you're going to do it with an inclined plane. I just wanted them to look at a piece and calculating the acceleration of a free-falling object, getting the speed of that object, graphing that information and collecting data and putting it in an organized manner into a data table. I got 2 cars, I got 2 tracks. You're going to go in 2 groups. Make sure you get a graph of the speed of your car, and also we're going to see if we can calculate the acceleration of your car. So by the end, you should have 2 graphs. Calculators, stopwatches. You guys got the sheet, read it, figure it out, keep going. With this age group, you have to kind of start these kids off with something that's a little bit more concrete and more solid for them to understand, and then you can kind of branch them off into the abstract and get them to formulate ideas and almost what I call take intellectual risk. We got our incline, okay? Check to make sure you're tight.
Don't we have to measure the angle, though?
That's why you got to read it.
How are we gonna find out the acceleration? You gonna tell us the formula?
Most definitely.
Okay, who wants to be the car holder?
But you got to find the speed first. Good question, dude. I think I started them with the ramp, primarily because it's kind of like most of these kids sled, they all snowboard. You got to really be on the trigger when it crosses your mark to get your time, okay? So this is why you got to make sure you do a couple trials before you just start collecting data. I toss a lot of variables at the kids because I think one of the goals as a scientist is that they're going to be bombarded with variables that will hinder experiments or procedural steps. And they have to learn how to control those and identify what's an independent and what's a dependent variable.
Neil, we need to figure out where it's
I got 303.
All right. Well, that's why you do more test runs. So.
I think when they realize that, they can say, oh, I need to control this and control this, control this, to test for just the one thing that I need to test for. Hey guys, Dobbies and Steph have a pretty good data table that we can use. If you guys in the other group check it out, once you have your distances of 1 meter, 2 meters, 3 meters, 4 meters, divide that time into your displacement, and what you will get is your speed or your velocity. If I gave them the table, they don't think. They need to be able to figure out ways in which to formulate and organize their information. That shows me how well they're thinking.
We're done. No.
Once you get done, you guys need to start getting this information and start trying to graph it. So we're trying to find out where that car is picking up speed and where it's changing its speed, which is going to be this acceleration. You got to make it clear. So just make it very simple. I think some of the kids were kind of confused on how to collecting and organizing the data, but that's an 8th grade piece, and I think one of the things that they'll start to develop as they get older and as become better scientists is to start to organize that information in a format that will be presentable for somebody else to duplicate and be able to read and understand. If you guys look at Christina's graph, we get 0.82 meters per second, and then our last one we got 0.85 meters per second, which means our car did what as it went down the ramp?
Accelerated.
It accelerated. What we'll look at next is we'll look at adding the mass in there, and then from the mass we'll look at momentum and see how well these cars will actually, what will happen to these cars when they have more mass. Now, how would we find the momentum of these cars?
It's velocity times mass.
Velocity times mass. What I need you guys to do for me is I need you to find the speed of these cars, okay? Once you find the speed of them, okay, we then got to figure out how we're going to get the momentum. I think if you can get kids active and motivated and, involved and get their hands and stuff, they're focused. I think that's what, kind of pulls them in and kind of gets them motivated. Plus just knowing who they are and having a relationship with them. Who needs me?
Do we need them? Nope. We make corrections on this thing?
I don't, let me ask. We use fractions? Or you want decimals? Decimals, dude. Decimals.
Decimamos.
Need errors.
I sometimes have to go outside my realm. And, the kids have to understand, too, that, they can be flexible in their thought process in formulating data tables because not every kid is going to think alike. See, now he's going totally different than what I just did. You figured it out. You figured it out one way, and there's nothing wrong with it. I figured it out totally different. Listen, I'm a simple-minded guy, so I figured it out this way. You're a genius, dude. So if you figured it out that way, God bless you, kid. Okay? And if it worked, it worked. That's great. Kids have unique ways in which to organize information and collect data and control certain variables. It's just a matter of how well they're able to collaborate with a group to come up with that ultimate goal. Darren, if I throw this ball at you, can you catch? Are you sure you can catch? Are you positive? Okay. I throw this ball. Would you try to catch this chair if it was coming at 30 miles an hour?
No. Too much momentum.
Why is it going to have too much momentum, Steve?
Because it has a huge amount of mass and it's going at the same amount of speed as all the other things, but it's more mass.
Beautiful. It's going to have much more mass, okay? And that's one of the things that I wanted you guys to really try to get and understand when you're looking at these different cars. So on the back of that sheet of paper, what I want you to try to do is I want you to answer those questions, and then I want to show you one demonstration. Let's just say I got this as a concrete wall. I got these little sand barrels. Okay? If you're driving in a car, okay, we got that little bounce back there. If I do this, okay, it bounces back a little bit, but it also this is going to absorb more momentum. Would you rather run into a nice concrete wall or some sand-filled barrels if you're in a car? Why, Darren?
Well, the concrete wall's going to be denser. It's going to have more mass.
Okay. It's going to have much more mass.
So it'll exert a lot more force back on you.
Good. It's going to exert way more force back on you. I just kind of wanted to see if they could make that transition and see that connection. And I think some of them did, but I still, it's something that you still have to revisit to make sure that they understand it.
George Mixon pushes his students' thinking by asking questions that get them to analyze data and test their hunches with one another.
Vygotsky pointed out that kind of assistance that will help development in the zone can come from more capable peers. It doesn't really matter where the assistance comes from. And the most competent teachers, I think, provide the assistance themselves when they need to, make sure that a good, rich diet of assistance is available from other class members and outsourced resources to make sure that's available to the student. That's the orchestration of excellent teaching.
At the Detroit High School for the Performing Arts, Ken Gillam's physics students study the same concepts, drawing on even higher levels of abstract reasoning. Through experimentation, they move into evaluating evidence, drawing inferences, and predicting outcomes.
I started what I knew was prior knowledge for them. We had done situations and had worked in situations where they had the opportunity to evaluate velocity, acceleration of a ball rolling down a ramp. We're going to use little bitty cars. Since we're going to do momentum studies and we're going to look at the momentum of the car, we have to have a mass to go with the velocity we determine. We're going to run it off the end of our ramp, let it go for a meter, and determine its velocity. We're going to take 5 readings. We're going to take 5 stopwatch indications so we know how fast the automobile is going when it exits the ramp. And I'm going to show you a collision. Their initial thought was, it's going to be the same lab again. Well, it really wasn't going to be the same lab again, because the minute I put a barrier there and crashed it, they said, this is not going to be the same. So the hook was, I think it's going to be the, no, it's not. And so I hooked them by giving them something they knew, but then giving them something new to look at. I want you to gather data on it. When that car bounced back a little bit, it moved a certain distance. Can we determine or measure that distance? I've chosen for you to work with 5 objects, and you're going to get to predict if you were going to be in an automobile crash and you were going to hit a barrier of some sort, what would you want the barrier made out of? Think about what occurs in a crash. What occurs in a crash? Someone tell me, Daniel, tell me what occurs in a crash.
Pain caused by the
force and momentum.
What else?
Pieces can fall apart off the car. Someone get hurt, somebody might die, depending on the type of crash it is.
So death can occur in these.
Mm-hmm.
One person from your groups, come, take the car with the crash materials that are there. Stopwatches are here, meter sticks are here, your towers to build your things are there. What we're going to do now is, once you get that, the first thing that you've got to determine is what? The velocity of your vehicle. They are ready to go into college, but in a lot of ways they're still just kids, and they like to see things that happen. When was the last time you got to play with toy cars in class and they called it work? So if you give them something on a concrete basis, this is concrete, you can take this car, you can roll it down this ramp, and you can make informational observations, you can collect data, you can use that data to develop information that is solid, meaningful in a problem-solving sense.
So when it hits right here, we start?
Yes.
Mr. Gillum. Acceleration
Yes.
from here to the end of the ramp.
What you're trying to do with these kids is you're trying to keep them involved in what they're doing, and you're trying to, every time, deepen the level of thought. But you got to start with something that they can put their hands on.
It moved back a little.
Can you determine a little?
I'm sure you could with the millimeter.
Yeah, if we put a ruler stick right there, how do we figure that out?
Well, you've got a distance. Can you time it from impact over a certain... Okay, do that. Once you see them beginning to fall into this pattern that says, we're all beginning to get this, then it's time to challenge them again. Move them up a level.
We concluded yesterday that since the energy and the momentum in the car could not be destroyed, that it was transferred from the momentum in the car's energy was transferred from the car into the foam block that we had.
So you take the solid concrete, then you take them into the problem-solving area, into the analytical, analyze what you've seen. Then, once you begin to analyze it, how are you going to use this information in a real world? How do you build these meta skills of thinking? How do you think in a broader context? Now you're going to design something to break down the momentum of an object as it is being hurtled down the road at 70 miles an hour with a mass of 2,000 pounds. Highway engineers have spent lots and lots and lots of time trying to figure out what's the best way to slow a vehicle down that is about to have a devastating crash. How many of you have ever been driving down the road and have seen the yellow barrels? Now, do you know that the barrels are filled? With what?
Water.
Yeah, they're filled with. Why?
To absorb most of the impact from the, well, in our experiment or whatever, you know, like the bounce of the wall. The car has so much energy going at a certain speed that once it hit it, you know, if it hit it dead on, it would stop.
If you hit something, I would prefer my car to go into it rather than to just hit it and bounce back, because that would hurt. But if your car goes into it, it will stretch. I mean, if the object stretches like some form of a putty or something, once it hits, the car will go in, slowing it down instead of just hitting it head on.
Okay, now we need to look at our equation one more time. We've got to remember, if I'm going this way and this way is positive, and then I turn and I go back in this direction and that way is negative, what is my change in velocity? V final minus V initial. My final velocity is positive minus a minus velocity makes the whole thing. Oh,
and they can begin to put together a pattern, a structure that builds into not only abstract, but into being able to bring it all together and synthesize something that may be totally unique in their analysis.
Understanding that you are really an instrument of learning and that you can help the child grow along all the developmental pathways, and that growth along all the developmental pathways is what makes academic learning most possible. If you can think that, then you will find all kinds of opportunities to help children grow and develop and learn both what it takes to be successful in school and as adults, and to get the academic material they need to be successful as adults.
Faye McLean, George Mixon, and Ken Gillum taught similar concepts using similar materials, but they adapted their lessons to the developmental needs of their individual students. They created intellectual challenges to support increasingly complex thinking. As a result, their students grew both in their competence and their confidence as learners. This has been the Learning Classroom. Thanks for watching.
Funding for this program is provided by Annenberg CPB to advance excellent teaching.